Okay, so in this part, we're going to make the character move, code the base movement for it without the animations, but we're going to set the foundation for our state machine with a parent move state that supports input recognition, etc. And we'll add some ground and some level element that the player can interact with. Okay, so we're going to create movement in a few steps. We're going to place down the base logic for our movement, how our character is going to move. We're going to do that in the physics process function. Remember that we have to remove the leading underscore in our state so that the state machine can call into that. So there, we're going to first calculate the input direction of the player. And for that, we'll use a function called getInputDirection. I'm going to add it under physics process. So we're going to create a static function there so we don't access any state. It's going to return a vector 3 here for the calculations in 3D to kind of work naturally, but we're going to calculate the input direction on 2 axes on the ground. So we're going to, well, for now, return vector3.0. It's a placeholder for now. We're mainly defining the main movement logic in our physics process function. Then from the input direction, we're going to calculate the actual move direction of the character. It's a bit different, I'm going to see. So let's create a move direction variable, and it's going to start just like input direction, except that we want the move direction to be normalized. The input direction can have a long vector because we can be moving diagonally, let's say. But when we actually move the character, we want it to move at the same speed if it's going diagonally or if it's going forward or to the right. And for that, we have to ensure that the length of the move direction vector is lower or equal to 1.0. So if it's too long, again, that happens when you go diagonally, we're going to normalize the vector. Move direction is equal to move direction dot normalized. It's a function that's going to make the vector at a length of 1, precisely. The last thing we could do is ensure that the move directions vector's y component is equal to 0. To explain why that is, it's because if you look in the 3D view, the ground plane is on the x and the z axes, and the vertical vector is the y-axis. So we want to make sure that this vector is always equal to 0 because in this function, we're only moving the character on the ground. So from there, we can calculate the velocity for the character. So for that, we'll need a variable called velocity, and it's going to be of type vector3. I'll initialize it to vector3.0. And in our physics process function, we're going to, on every frame, calculate the velocity. So we'll create a function for that. Again, calculate velocity. I'm going to create that placeholder function at the bottom of my script. Function calculate velocity. It's going to return a vector 3. And we're going to return, again, vector3.0 as a placeholder for now. So we'll calculate the velocity, and then we'll move and slide the character. So it's a function, move and slide, that's on the kinematic body class. It requires a linear velocity, so that's the value that we're calculating above. That is a speed in a given direction. And this function, move and slide, will transform it into a motion by, inside the function, multiplying our velocity by delta. This is why we don't multiply velocity by the delta value. The function will do it for us internally. Then it takes the normal of the floor. This is something you can use for slope movement, slope detection. So we're going to set that to vector3 dot up. This is going to be a vector 3 with the y component set to 1.0. This is a vector that's going to look like that. Straight, of course, because it's not drawn with the mouse. But That's it for our base logic. We're going to do one last thing, is that move and slide function, it returns a new velocity, depending on the context where the character is moving. And so we want to assign that velocity to our velocity variable. You can control click on the function to jump to its documentation, where you have a lot more details. But the point of what we're doing here, assigning the new velocity to the variable and overriding our velocity, is that when the character is falling and touches the ground, move and slide will reset the y movement with the y velocity to 0. Even if we're just calculating movement on the ground, we'll also apply gravity to our character automatically at all times. And this call here, this move and slide function, will make sure that if the character is on the ground, the gravity gets reset on every frame. We're going to add one last thing. It's rotating our character if there is a move direction. So if move direction, the vector, you could check if the length of the vector is greater than a small value. It means that player is pressing a key. Or now in the latest version of Godot, you can directly write if move direction, and it will take into account the floating point value uncertainty for you. It will basically check that the vector is longer than a very, very small value. In that case, we can turn the player around, and it turns out there's a function called lookAt on spatial nodes that we can use. So we look at a target point, and that point will be the character's position. So it's player.globalTransform.origin. This is the origin of the character in global coordinates in the world. And we'll add our move direction to that. So we'll look at a point relative to the character. And the up vector is going to be the same as in our move and slide function call, vector3.up. So the y-axis pointing up.